So hello everyone, welcome back to our channel, and in today's live stream we are going to be continuing with our topic of digital electronics, and today we're going to be studying about counters and digital memories, right? So let's get started with it. In the last lecture we had seen the different types of sequential circuits, in which we started off with flip-flops, and then we continued on with the resistors, right? So today we're going to be talking about counters, right? Okay. So now what basically is a counter? When I say the term counter, what does it mean? Right? So what is a counter? Counter is also a sequential circuit. Counter is a sequential circuit, and it is a logic circuit which is capable of counting. As the name says, it is capable of counting. So it will count the number of clock pulses which will arrive at the clock input. So what will it do? It will count the number of clock pulses, right? So now let's move on to the basics of counters. So basically a counter having n flip-flops. Let's consider n flip-flops. A counter having n flip-flops will have maximum possible states which are represented with capital N would be equivalent to 2 raised to n, right? 2 raised to n. If if there are two conditions to this, if capital N is equal to 2 raised to n 2 raised to n, then we call this a binary counter. Then we will call this a binary counter, right? And when n is less than 2 raised to n, then we would call it a, what would we call it? We would call it a non-binary counter, right? So basically what a counter can do is, it can basically count from 0 to 2 raised to n minus 1. A counter can count from 2 raised to 0 to 2 raised to n minus 1. Now what is a mod number? Mod is nothing but the number of states present in a counter is known as modulus counter or a mod counter. So mod is nothing but the number of the states that are present in the that basically the counter counts, right? So for example, if there are n flip-flops in a counter, it will have 2 raised to n different states. As I said, if it consists of n flip-flops, then it will have 2 raised to n different states. Then we can call this counter as mod 2 raised to n, mod 2 raised to n counter. Then what will we call it? Mod 2 raised to n counter, right? Now let's move on to understanding a mod m counter. One second, I will draw a simple diagram of mod n counter. Let me just okay. So basically, if let me just draw a block diagram. So we would call this a mod n. One second, we will call this a mod n counter, right? So what this counter would do is, so mod number indicates the frequency division obtained from the last flip-flops, right? So we can say that if the input as frequency f, then the output frequency would be f divided by n, right? Very simple to understand. If input is f, then the output will be f by n, right? So input frequency is f, output frequency is f by n, then the overall states, what are the overall states over here? Overall states are n, right? Now you guys tell me, there's a question for you. In this case, we have considered only one counter mod n. If we consider two counters, this is a counter mod n, this is mod n counter, and let me consider one more counter over here. This would be mod m counter. Then, and if these are cascaded together, these are cascaded together, these are cascaded in together over here and over here, right? Then you guys tell me, if mod m and mod n and m counters are cascaded together, then what would be the input frequency and the output frequency, and what would be the overall states of combined counter? You can pause the video and try answering. Okay, I will give you the answer. The input frequency will be f itself, but the output frequency will be f divided by m into n, right? Because the overall states would be m into n. These are the overall states. In the above case, when there was only one counter, the overall state was capital N, right? So these are the different types of counters. Now let's try classifying the counters. Right? So let's classify. We all know that there are two types of counters. One is the synchronous counter, and what is the other one? The other one is asynchronous. Very good. The other one is asynchronous counter. Right? Now let's see what is the difference between a synchronous counter and a asynchronous counter. Yes. In a synchronous counter, as the name says, all flip-flops are triggered using at the same time using the same clock pulse. Right? Same clock. All flip-flops are triggered using the same clock pulse. Whereas in case of a synchronous counter, it is different flip-flops, right? Different flip-flops will have different clock pulse. Different flip-flops will have different clock pulse. This is the first and the main difference, right? Then what is the, obviously since it is a synchronous counter, it is fast. It is faster, right? And this is a little slow. The second asynchronous counter is a little slow. What could be anything else? Yes, a synchronous counter is a little complex to design, and a asynchronous counter is easy to design. So these are just three, 4 points difference between a synchronous counter and a asynchronous counter. Now there are two types of counters. Let's look at the up counter, right? So this is a type of a asynchronous counter. Ripple counters are this diagram you can see over here. This is the diagram of a 3-bit ripple counter, right? Now the ripple counter is nothing but a asynchronous counter, right? So as we all know, different clock pulses applied to different clock pulses applied to different. You can see over here. This is the clock pulse. It is applied at different intervals from different inputs, right? And in a asynchronous counter, the flip-flops is applied with external clock, which also acts as the LSB. You can see over here, this is the LSB, the first clock pulse. Now, in here you can see that the input clock is applied at the LSB and it is a n-bit ripple counter. Then the maximum states will be 2 raised to n. In this case, it is a 3-bit ripple counter, right? So that means the n, small n, 2 raised to n is, there are 3 flip-flops, right? Okay. Now, if all states are used with the input frequency f, then what would be the output frequency? We all just saw. If the input frequency is used with f, then what would be the output frequency? The output frequency will be nothing but f divided by 2 raised to n. And in our case, since it is 3-bit, the value of n will be 2 raised to 3. Right? Okay. Now let's move on. This was nothing but the block diagram of a upper 2-bit upper 3-bit upper counter. Now this is just a asynchronous down counter, right? Now this will count in the opposite direction, right? Now if the now how do you decide whether it is a up counter or a down counter? It is very simple, using the clock pulse given over here, right? So if it is a negative trigger, you can see over here there is this bubble over here, you can see on each flip flop, and in this diagram there is no bubble. So what does the bubble indicate? Yes, a bubble indicates positive edge triggered and negative edge triggered. So whenever we say there is a bubble, whenever it is negative triggered or negative edge triggered, it acts as a down counter, and when it is a positive triggered, then it is acting as a up counter. Right. So this was about the counters, very simple. Now let's move on to the next topic, that is the different memories that we have. You can see over here the memories can be classified into 4 types: primary memory, secondary memory, cache memory, and registers. Right. Now in your main we are going to study the primary memories and the secondary memories, and very specifically, most importantly, primary memories are something that we are going to study. Right. Now registers are the fastest. Okay, registers are the fastest. But now let's look at the detailed classification of primary memories. So primary memories are again classified into 2: RAM and ROM. What is the full form? You might be knowing. RAM is random access memory and ROM is nothing but read-only memory. Right? So there are 2 types of RAM: static RAM and dynamic RAM. And in types of ROM, we have PROM, EPROM, and double EPROM, right? Or it is also called as E square ROM. Now let's look at the different comparison points between this static RAM and dynamic RAM. The very first thing is, in case of static RAM, the data is stored in flip-flop like a structure. Whereas in case of dynamic RAM, it is stored as a mass capacity. So basically what we can say is static RAM is faster and dynamic RAM is slow, right? In case of static RAM, there is no refreshing required, whereas in case of dynamic RAM, there is refreshing that is required. Now in case of read only or ROM memory, so basically ROM memory is nothing but a combinational circuit, right? And it is also known as masked memory. It is also known as masked memory. So we can do the comparison of memories as, so if it is a ROM, a simple ROM, then we can say it is fixed and fixed OR, right? If it is PROM, over here you can see if it is PROM, then PROM is nothing but fixed and fixed and fixed and programmable programmable or in case of PROM, in case of PROM. Now if I consider PAL, programmable array logic, and programmable logic array, these are also 2 types. Now in this case we can say that we have programmable and but we have fixed or. But over here in PLA we have programmable and programmable or. Both logic functions are programmable. So this was about the memories in very brief, right? Now let's move on to revising the next concept, that is nothing but digital to analog converters and analog to digital converters, right? So this is possible to convert the analog signal into digital signal or vice versa, right? The very first thing that we are going to study is we are going to convert digital signal to analog signal. Now you can write it in the comment box. Why do we need this conversion, right? So let's see. Look at this. This is the simple block diagram. So in this block diagram, we can see that there is n binary input that we can give, n bit binary input that is given as the input, and we would get the equivalent analog output, which is also called as VO, right? Which is also called as VO. So this is the basic block diagram which is telling us that n bit is going to be converted into VO equivalent analog output. Now you can see this is the basic classification of a digital to analog converter. Okay, now there are different types. The very first type is the weighted resistor D to A converter, and the second one is R to R ladder. Now what you need to know is, you just need to know two things about this. The very first thing is the circuit diagram you need to know, and the second thing you need to know is very important, the output equation. You need to know the output equation and the circuit diagram of each type. Okay, this is what is required in your exam. That is why this is a quick revision series. That is why I am going to show you the different formulas. You can take a screenshot of it, or you can draw it, pause the video and draw it in your what do you call this, in your notebooks, right? So let's look at the very first type. This is the very first type, which is called as the n bit. Yes, you can see this properly. This is called as the n bit n-bit weighted resistor. This is the block diagram. Yes, so you can see over here we are using an inverting op-amp, right? Now this inverting op-amp is parallelly connected to four resistors from starting from R to n minus 1, right? And these are the four bits, different bits starting from B0 to B raised to n. Right, now you can see B0 is also, or the 2 raised to n minus 1 is also called as the least significant bit, right? So this is the basic diagram of n bit weighted resistors. So we are using different resistors are connected which has different weights, and the weight or the value is decided based upon the n value. So very first important thing is this diagram that you have to know, and over here you can see the LSB resistance. You can see over here LSB resistance, a formula that is nothing but 2 raised to n is the MSB resistance formula. And what is the MSB resistance? What is the MSB resistance? Yes, MSB resistance is only R. Okay. Now let's move on to the next type, that is called as the R to R ladder. Now you can see there is a ladder that is forming using a R resistor and 2R resistor. You can see over here. The LSB is nothing but 2R resistor. Then we have alternate R resistor connected. Then again 2R, again R resistors. So R and R2R resistors are connected in alternate manner, right? And this is the formula which is very important. You have to know. I have just see, this is a short notes that I am displaying over here. So I'm just telling you what are the different important points that you need to know for your quick revision, right? So you can take a screenshot and draw this diagram in here. Again, we are using the inverting op amp over here, and this is the formula which is nothing but, what is the formula you can read over here? V0 is nothing but, or V output is nothing but VR upon 2 raised to n summation of I equal to 0 to I raised to I equal to 0 to I is to n minus 1, 2 raised to I, b suffix I, b is nothing but bit, into bracket 1 plus RF upon RI. RF is nothing but the feedback resistor over here at the top, you can see connected to the op amp. So this is the output formula of a R to R ladder DAC, right? Very simple and easy to understand. These are the two important points that you need to understand, right? Now this is also very important from your exam point of view. You need to know the different specifications of DAC. Now there have been many previous year questions that they have already asked, where the direct formula has been used, and using this direct formula you can get to the answer. The very first one is the resolution in a DAC, right? So what is it? Resolution in a DAC is changed in analog output with corresponding to the first LS bit, least significant bit increment at the input. So it is nothing but V resolution is nothing but given as VR divided by 2 raised to n minus 1, where VR is nothing but the voltage corresponding to the logic and n is nothing but n number of bits. Now let's move on to the next. What is nothing? This is nothing but analog output. So the value of analog output is nothing but resolution into decimal equivalent binary data, right? Decimal equivalent binary data. Now next is maximum analog voltage output. Now this is also given as VFS, right? Full scale voltage. FS is full scale. So it is nothing but maximum analog output of a DAC. The formula is VR divided by 2 raised to n minus 1 into 2 raised to n minus 1, which is nothing but equal to VR. So what does our VR? VR is nothing but the voltage corresponding to the logic. Okay. Now next is percentage resolution. This question has been asked in previous year question. In the last session, in I guess the yesterday's session itself, we tried solving some previous year questions in which we had used the same formula. It is nothing but the resolution percentage of a digital to analog converter is nothing but 1 upon 2 raised to n minus 1, right? And what is the last specification that you need to know? In case of a R2R ladder type, specifically the resolution becomes VR divided by 2 raised to n, right? Yes, and this thing was also you need to remember, the maximum error acceptable in a ADC and DAC is equal to the resolution. This is very important, you need to understand. So these were the specifications of DAC. Now let's move on to the, just give me a second, let's move on to analog to digital conversion, right? Yes. Okay. Yes, over here let's look at the block diagram first of an analog to digital converter. Yes, so you can see there is an op amp that has been used, then there is a AND gate, and then we have used a clock counter which is connected to a digital analog converter. So this is called as a counter type ADC, where we have used a counter in the circuit, right? So this is just a basic block diagram to analog to digital converter. Now these are the key points that you need to remember. First one is, in a end bit counter type ADC, the maximum number of clock pulses required for conversion is nothing but 2 raised to n minus 1, right? Now next, what is the maximum time required for conversion? It is nothing but 2 raised to n minus 1 into T clock. T is nothing but time period, which is also given by 1 upon f, right? This is something you need to remember. Now the maximum number of clock pulses is 1, and the average number of the minimum number of clock pulses is 1 obviously, and the average number of clock pulses is 2 raised to n minus 1. Now this is the first type of analog to digital converter, which is called the successive approximation, right? Now it is faster than the digital ramp ADC, and the conversion time is dependent upon the analog input voltage. So you can see over here there are two terms, SOC and EOC, which means start of conversion and end of conversion. Now in here over here you need to remember this formula, which is nothing but called as the maximum conversion time. That is nothing but number of pulses required for conversion into the time period of each clock, right? Time period of each clock. So this was the first thing about the analog to digital converter. Now let's look at the next type. Yeah, now this is the flash type. So basically this question also has been done. The flash type is also called as a parallel comparator type ADC, right? And it is also called as the simultaneous converter, and it has the highest speed, right? Okay. Now this is something you need to remember. Like for an n-bit comparator, the total number of comparators are required are 2 raised to n minus 1, and the total number of resistors are required in the formula is given by 2 raised to n, right? So this is the circuit diagram of a 2-bit flash code converter, right? And then we also require a priority encoder because it is required, and the number of priority encoders are required. The formula is given as 1 into 2 raised to n into n, right? So these are three formulas that you need to remember in case of a flash converter. all they can ask you a very simple MCQ based on this. They will just give you that we need to convert a 4-bit, we need to construct a 4-bit flash converter. So what are the total number of comparators required, what are the total number of resistors required, and what are the total number of priority encoders that are required. So this is a basic circuit diagram of a 2-bit encoder. So let's count. In case of a 2-bit flash converter, we would require 2 raised to 2 minus 1 comparators, right? 2 raised to 2 into 2 raised to 2 minus 1 n comparators. We would require 2 raised to 2, that is number of resistors, and we would require 1 into 2 raised to 2 into 2 number of priority encoder, right? So you can see over here 2 raised to 2 minus 1 is 3. So you can see there are 3 comparators in here. Then 2 raised to 2 is nothing but 4. That means you can see over here there are 4 resistors that have been used. Then we have 2 raised to 2 into 2, that is you can see over here 4 is to 2 comparators, right? Okay. Now we can see the next type, which is also called as dual slope integrating type. Uh, Dual slope integrating type analog to digital converter. Now in here you have to know the formula. Okay, where's the formula? One second. Yes, the formula is over here. Okay, no, one second. I will just show you the formula. Yes, this is the formula that you need to know. VA is equals to VR divided by 2 raised to n into n, where n is nothing but count recorded in the converter. Now you can see the basic formulas that are required for a dual slope integrating type DAC. The first one is total number of clock pulses required is nothing but 2 raised to n plus 1, right? And the maximum number, now we are talking about maximum number. It is nothing but equivalent to 2 raised to n plus 1, approximately 2 raised to n plus 1. Now see, this is just a simple table which is telling us these are the different types of ADC that we covered. The first one is a counter type, yes. Then we saw the second one, SAR, that is nothing but successive approximation type. Then we have the flash type ADC, flash converter, and then the last one, that is dual slope. So in case of counter type, the maximum number of clock pulses required is 2 raised to n minus 1. For successive approximation, it's n. For flash type, it is 1. And for case of dual slope, it is 2 raised to n plus 1. Right? And what is the feature? The flash type is the fastest and the dual slope is the most accurate one. Right? Dual slope is the most accurate one. So in this manner, we have completed the types of memories and we have seen the different types of digital to analog converters and analog to digital converters. Right? So in this very brush up of all the concept, I've also told you what is very important. In case of analog to digital converters and digital to analog converters, two things are very important: the circuit diagram and the formulas. Right? So in this manner, you have to understand and you have to remember these specific things, because while solving the questions in our exam, you need to remember these formulas. If you know these formulas and if you have by hearted these formulas, you can easily solve the MCQs in less than few seconds, right? And that is what we want for the examination, right? So with this note, I want to tell you, if you have any questions related to digital electronics or the whole ESE preparation, you can put it in the comment box. And there is a link given to the telegram channel, in the description box. Make sure you join the telegram channel, because we keep updating with our notes over there, and we also keep you posted with the timetable of our videos, right? So make sure you join the telegram channel to have all the access of to the notes, and in such manner we are going to complete the whole syllabus with a very quick revise for our engineering services examination 2024, right? So with this note, I will take your leave and I will see you all in the next lecture or in the next live session. Thank you so much everyone for joining. Thank you.